The first speaker of today's lecture series in connection with the Platinum Jubilee is Professor Supurna. To say a little bit about the speaker, Professor Supurna did her bachelor's in physics at Jadavpur University, Kolkata. She completed her master's at the physics department, Syracuse University, where she did her PhD in non-equilibrium statistical mechanics with MC Marchetti. Currently, she is a professor at theoretical physics at the Raman Research Institute, and she has different areas of expertise, including non-equilibrium statistical mechanics and quantum information. Her work in the area of quantum Brownian motion has led to predictions testable in ultra-cold atoms labs. And in the current talk, she will be speaking about random walks in physics, a perspective. So let's all welcome Professor Supurna to the podium.
So I would like to thank the organizers of this Platinum Jubilee event for inviting me to talk at this forum. So the topic of my talk today is random walks in physics, a perspective. A random walk or its continuum limit, Brownian motion, has been a common thread in a lot of my research at RRI over the years. I will highlight some of my research work where it has appeared. So the topics that I intend to touch upon are Brownian motion and magnetism, the worm-like chain model of biopolymers, focusing on DNA elasticity, active Brownian dynamics, surface tension and the cosmological constant, decoherence at absolute zero, and Brownian motion at absolute zero. So a random walk in one dimension is generated by coin flips of a fair coin. The walker takes steps to the left or right depending on the result of the coin flip. The continuum limit of a random walk is Brownian motion. For instance, movement of milk globules kicked around by surrounding water molecules is an example of Brownian motion. I will mention some of my work where these notions have appeared. So Brownian motion and magnetism. So the question of interest is the following. Given a Brownian particle moving on a plane which returns to its starting point, what is the distribution of areas? This led to a natural connection between the area A and its conjugate variable, the magnetic field B, and led to an interesting observation on diamagnetism of bosonic systems. So if P of A is the distribution of areas, P tilde of B, which is the conjugate distribution, is given by this Fourier transform. And P tilde of B is called the generating function for the distribution of P of A. Since by taking derivatives of P tilde of B, you get various moments of the distribution. And P tilde of B can be cast in this form as the ratio of the partition function in the presence of a magnetic field and the partition function in the absence of the magnetic field by making use of the Wiener path integral for Brownian motion. Thus, an insight into magnetism appeared as a byproduct of studying the distribution of areas of closed Brownian paths. This was work done with Joseph Samuel, appeared in Physical Review B in 1994. Actually, the central question of interest in that work was the distribution P of omega of solid angles described by a closed Brownian path on a sphere. And this is closely related to depolarized light scattering. So you have a light beam which gets scattered off various centers in a random medium, and there is a depolarization which happens to the light beam, and the extent of depolarization is captured in terms of the solid angle. This is solved via the mapping that I alluded to earlier, and in this context the relevant magnetism problem is a monopole located at the center of the sphere. And one can compute the partition function, which is of this form, this summation form. And in order to compute the distribution of solid angles, all one needs to do is to take an inverse Fourier transform, and you get an expression of this form, which can be plotted via Mathematica. And this is a family of curves of P of omega versus omega for various values of beta. Here the parameter beta has the interpretation of the total time taken by the Brownian walk. So you notice that for short times, the distribution is peaked around omega equal to 0 and omega equal to 4 pi. reflecting the symmetry of the sphere. And as time progresses, the distribution flattens out, and all possible solid angles are explode with equal probability. So now we come to diamagnetism. We consider n spinless bosons and consider the area enclosed by their trajectories, where we allow for exchanges of particles. And we consider the area enclosed script A, and the probability distribution P of A, which is given by this delta function, expectation value of the delta function, which picks out areas of size capital A, is related to the conjugate distribution P tilde of B, which I alluded to earlier, via a Fourier transform. Now, notice that P tilde of B is the Fourier transform of a positive function, because it is the Fourier transform of the distribution of areas, and that is clearly a positive function. This imposes certain constraints, and one of the outcomes of that is an interesting inequality, that Z of B is less than or equal to Z of 0. And this gives an upper bound on the partition function, or equivalently, in terms of the free energy, one can write it as f of B is greater than or equal to f of 0. The free energy in the presence of the magnetic field is greater than the free energy in the absence of the magnetic field. And this flipping of the inequality happens because of the presence of the negative sign between the free energy and the partition function. And this is clearly a statement of diamagnetism. So another inequality also comes out from the same constraint on P tilde of B being the Fourier transform of a positive function. So there's another condition, which is P tilde of B is greater than or equal to cosine of pi B over 2 B sub C. P tilde of B, remember, is the ratio of the partition function in the presence of the magnetic field and in the absence of the magnetic field. So thus, this inequality gives a lower bound on the partition function. So that corresponds to an upper bound on the free energy and puts a constraint on the extent of diamagnetism. So in the earlier slide, we found that there exists diamagnetism, but this other inequality is constraining the extent of diamagnetism. And thus, the possible values of the ratio of the partition functions possible values lie within this allowed region enclosed by, or the two boundaries are given by the straight line parallel to the B axis and the other curve which comes from this inequality. And we considered an illustrative example of a charged particle in a magnetic field, charged harmonic oscillator in a magnetic field, and we found that the solution indeed lies in the allowed region. So the next thing is a Gaussian for diffusion on a sphere. So the probability distribution for diffusion on a plane, as many of you would know, is given by a Gaussian expression like this. So the question of interest is, what is the counterpart of this on a sphere? And we used a saddle point method to arrive at a short time propagator, which is non-perturbative in the spatial domain. In the context of the sphere, the spatial domain corresponds to the polar angle theta, and arrived at an elegant expression for the distribution function, which is essentially a Gaussian modulated by a prefactor square root of theta sine theta. So this was work done with Abhijit Ghosh and Joseph Samuel and appeared in Europhysics Letters in 2012. And a few things I wanted to highlight about this work. We obtained an analytically elegant Gaussian probability distribution formula for diffusion on a sphere, Gaussian within quotes because of the prefactor. This formula also leads to an efficient algorithm for simulating diffusion on a sphere, which improves on the standard tangent space approximation based algorithms, since it takes into account the curvature of the sphere. So in the tangent space approximation, at each point on the sphere, you approximate it by a tangent plane, whereas here you are actually taking into consideration the curvature. This leads to a more accurate computation and also more efficient, because you have to take fewer steps in time. this formula allows for a generalization to saddles and other curved manifolds, which have many applications in soft matter and biological physics. Then we come to the worm-like chain model of semi-flexible polymers. In the worm-like chain model, a semi-flexible biopolymer molecule like DNA is viewed as a curve in space. So this is a curve in space, and at each point you can assign a tangent vector. So so you can think about the single polymer molecule. It gets jiggled around by thermal fluctuations due to the ambient medium and samples various different possible configurations for the end-to-end distribution. And it turns out that it is convenient to write the end-to-end distance distribution in terms of a Wiener path integral for Brownian motion on a sphere. So you formulate the problem in the tangent space. In the space, the sphere is spanned by the various tangent directions that characterize the polymer molecule. And the elastic properties of such a polymer can be computed very effectively by using this mapping. You can compute the end-to-end distribution and also the force extension curves, and which are experimentally testable. And not only that, there have been single molecule experiments on DNA and other biopolymers where we find excellent quantitative agreement. So just to highlight a few of my papers in this area, some written in collaboration, others single author, and the most recent one in this series is ring closure in acting polymers, which I wrote with Shebamti Chattopadhyay, who is there in the audience, Physics Letters A in 2017. So active Brownian dynamics. Active Brownian particles are self-propelled particles which generate dissipative directed motion by consuming energy from the environment. For instance, bacterial run and tumble motion is an example of that. The speed of an active Brownian particle is fixed, but its direction is a vector diffusing on the unit sphere. So we again come back to Brownian motion on a sphere, and I used this mapping to compute the orientational probability distribution of an active Brownian particle. And I would also like to point out that the dynamics of an active Brownian particle, while it is essentially the same as the problem of Brownian motion on a sphere, also maps to the problem of equilibrium statistical mechanics of semi-flexible polymers, which that mapping I had alluded to in an earlier slide. And this is a plot of P of theta versus theta for at short times, and it agrees very well with the exact probability distribution that one can compute by using spherical harmonics. And this short time approximation turns out to work well even at intermediate times. And I had also computed it in the long time limit using a long time, extremely long time approximation, which again agrees very well with the exact probability distribution. So between these two approximations, one can cover the entire spectrum of times. So this paper that I wrote was published in Journal of Statistical Mechanics, Theory and Experiment. And the predictions of this work are testable in experiments on Janus colloidal particles, which consist of particles which are composed of which have two different distinct chemical compositions. Yeah. Theta is the angle. Theta is an angle. Actually, this is just you can plot it in terms of radians or degrees or whatever. Yeah, I mean this is just a choice of angles that have been chosen for the Mathematica program. Yeah. So then we come to surface tension and the cosmological constant. So a small non-zero value of the cosmological constant stemming from the discreteness of space-time on quantum gravity scales was predicted by Sorkin, So the idea is to assume a mean zero value of the cosmological constant and generate a finite small non-zero value of the cosmological constant by making use of the discreteness of space-time on quantum gravity scales. This was predicted by Raphael Sorkin. So we proposed a soft matter analog of this effect, where we find a small non-zero surface tension of a fluid membrane stemming from a finite number n of amphiphilic molecules. And this has been covered in two papers, one with Joseph Samuel in PRL and another with Rohit Katti and Joseph Samuel. And I want to make one important point here. In the context of quantum gravity, the energy scales are not probable. Whereas in the soft matter counterpart, one can actually do an experiment and see this concretely, this fluctuation effects being borne out. So that's the advantage of the analog. And one more, and there are similarities and differences. In the context of the fluid membrane is naturally an example where the mean surface tension is zero. And this is actually there. And you can generate a small non-zero value by considering a finite size fluid membrane with a finite number of amphiphilic molecules. In the context of the quantum gravity context, the mean zero was considered to be an assumption, and assuming that, how one can generate a non-zero value. So there are these comparisons that I just thought I should make. And this is an example of fluctuation effects playing a role and akin to Brownian motion. And decoherence at absolute zero. Decoherence plays a central role in understanding the quantum to classical transition, and the model that is used is the same as the system plus environment model that is used to study quantum Brownian motion. So around the time that I addressed this question, I was somewhat unhappy with the treatments that were available at that time. Decoherence studies invariably invoked a high temperature classical limit for the bath. So as if one needs to rest on classical mechanics to address the problem of measurement. So I wanted to understand, my central question was, is there decoherence even at absolute zero, where only quantum fluctuations are present? I want to mention one thing. I think yesterday in one talk it was mentioned that journal clubs have played a seminal role in driving research at RRI. And this particular work that I did was triggered by a journal club. I mean, I took up the one paper by Zurek, and I thought that this is a somewhat unknown area for me. Let me read it and present it to the audience. And after preparing it, I realized that this is a question that one can address, and this research problem really came from the journal club. So the central question is there decoherence even at absolute zero, where only 0-point quantum fluctuations are present? So the answer was yes, indeed. Notice that the law, there is decoherence, and notice that the law is distinct from the usual high temperature exponential decay of decoherences. This paper was published in Physics Letters A way back in 1997, and I obtained a power law decay of decoherence, decay of coherence. The off-diagonal elements of the density matrix falls off like a power law, and the power being given in terms of this expression, which is independent of the temperature. And it turns out that such a slow decay of coherence is testable in cold atomic systems, and there is a paper by Sarkar et al. In PRL 2017, where they have noticed non-exponential decay in the very low temperature domain dominated by quantum fluctuations. Brownian motion at absolute zero. Brownian motion is as we have already discussed, is the random motion of particles suspended in a fluid resulting from their collision with fast-moving molecules in the fluid. At room temperature, the law of diffusion is given by the well-known Einstein's law of diffusion. where the mean square displacement grows linearly with time. So the question is, what happens to this law of diffusion as we lower the temperature to close to absolute zero and scale down the size of the particle? In the quantum domain, we find that the mean square displacement goes logarithmically with time. The initial work was done with Raphael Sorkin way back in 1992, and it was published in Physical Review B. And more recently, Urvashi Satpathy, Raphael Sorkin, and I published an improved version of this theory. It has appeared in Journal of Statistical Mechanics in 2018. So our derivation makes use of the fluctuation dissipation theorem. Fluctuation dissipation theorem connects the correlation of fluctuations with response function, in particular dissipation. For instance, Nyquist theorem, where the mean square voltage fluctuation gets connected to the resistance, is an example of fluctuation dissipation theorem. And it is independent of the details of the system, and that's its strength. Sorry. Yeah. Recently, there has been a theory experiment collaboration with the LAMP group analyzing the response function of a cloud of cold atoms. And this sets the groundwork for testing the predicted logarithmic law of diffusion in the deep quantum domain. So the reference is Optics Continuum in 2022, this year. Work done with Shubhajit Bhar, Maheshwar Shah, Urvashi Satpathy, Raphael Sorkin, Saptarishi Chaudhuri, and Sanjukta Roy. And there's continued collaboration in this area. So I have continued interest in the area of quantum Brownian motion and also decoherence at very low temperatures. So here are some of the papers that have been published and appeared recently. My collaborators in this effort have Shuraka Bhattacharjee, Kaushik Mandal, Urvashi Satpathy, Abhijit Das, Abhishek Dhar, Ayan Satra. These are the people who have collaborated with me in this particular area. And just to conclude, a common thread in many of my research projects at RRI has been Brownian motion. Brownian motion and magnetism, a connection. Brownian motion on a sphere, the WLC biopolymer model, a Gaussian for diffusion on a sphere, active Brownian particle dynamics, surface tension and the cosmological constant, and which involves root-end fluctuation effects, decoherence at absolute zero, Brownian motion at absolute zero, and there's continued interest in theory experiment collaboration with the LAMP group, Saptarishi Chaudhuri, Sanjukta Roy, and others. More recently, applied to a charged Brownian particle in a magnetic field. That this work I've done with Urvashi Satpathy and Shuraka Bhattacharjee, and a spin in a magnetic field, which I've done with Kaushik Mandal and Shuraka Bhattacharjee, and the last one being motivated by spin noise spectroscopy experiments and spin coherence experiments in cold atoms, which have happened already in Saptarishi Chaudhuri's lab. So, thank you.
Thank you, ma'am. That was a nice talk. If you guys have any questions, you can ask.
So I was just wondering that when you are talking about this diffusion on a sphere, so theoretically, like if you increase the curvature of the sphere, does it smoothly go to
Yes,
plane?
that's correct. Exactly. In fact, you can just see that if you just go back.
Increase
Yeah. See here.
Yeah.
Yeah. Here you see that when for small angles, sin theta goes over to theta, and you're left with that theta, which is the counterpart of r in that expression. If you look at the first expression, p r comma t is r over 2 dt. So theta plays the role of r here, and so it goes over to.
Thanks.
Actually, continuation of my previous similar link to diffusion on a sphere. So I'm trying to physically understand. So when you say that if you go to a large angle, if I understand your definition of angle correctly, then the diffusion actually goes down, is it? The probability
No,
of
you
diffusion.
are talking about this. This is slightly different from that. Okay, I'll tell you. You are talking about.
Yes,
this,
I am.
Yeah,
Yes.
this is basically you think in terms of the active particle
Yes.
dynamics. So you look at the angular distribution, probability distribution for that. So yeah, this is the way it happens. This is a short time approximation. In the short time approximation, this is the way it works out, and it has been borne out by simulations also.
Okay.
Actually, I have one question. Why do you think this queuing happens towards the left? This.
Yeah, it's a skewed distribution. This is actually closely related to the slide that I had shown earlier. It basically, if you take this distribution, it will also have that kind of a feature.
I have done similar experiments in optical tweezers with upconversion particles.
Okay.
So upconversion particle is emitting at a 975 nanometer, and when we trap the upconversion particle from the bottom, like we are trapping from the side, and it's tried to push away. And when we took the time series, we saw excursions in time series, and when we plot the probability intensity distribution, it was showing a similar skewness.
Okay.
And
Skewness it noticed. So that is consistent
skewness
with
was
the
there,
skewness,
consistent with this theory. But that time we couldn't fit any expressions to that.
Okay,
scale.
I would like to discuss with you.
Okay, sure,
Yeah,
we'll discuss.
please.
Yeah. Okay. So if you guys don't have any questions, we'll move on to the next speaker. It was nice.